So, good afternoon, everyone. Thank you very much to be with us. It's a great pleasure to have today with us a distinguished scientist, but also a friend and an ex-student. We can consider, Pete, George Kavulakis and George Kakavelakis like an ex-HMU student, because when he was he was doing his PhD in Imperial College in the physics department, we had organized a summer school in organic electronics, and Pete was one of the most active students in night and also during the morning, like during the lectures. Pete, he has obtained his PhD in Imperial College in London under the supervision of Thomas Athopoulos. I think that you know also Kaliakatsos, that he was visiting Imperial the period that you were. Pete, I don't remember well. And
Yes.
And his research interests are polymer electronics, semiconductor devices, organic photovoltaics, and solar energy. His work has received more than 2,500 citations, and his H index is 21. Now, Pete is a research group leader and an assistant professor at VSTEC. I cannot pronounce the whole name, so I keep the acronym, in Thailand. So we are very happy. Pete is always very supportive on whatever we are doing, however far away is now from Europe or from Crete or from London. Pete, the floor is yours, and thank you again.
Hi, good, I think, is it morning, yeah, in Europe? Yeah, good morning, everyone. Um, so thank you very much, Costas, for inviting me to join this series of Athena talks. I myself also listened to a few before, and I'm very honored to be one of the speakers of the series. And very nice to see Anis and all the others that met before as well. And let me start sharing my screen. Okay, so I will talk about insights into this particular material, copper-1 thiocyanate, which I have been working with since my PhD times. It's been, I think, actually more than 10 years already. I think we started investigating this one in about 2011. It is a semiconductor with a unique set of properties, highly transparent, okay, and it's p-type. Inorganic p-type is actually quite rare, and this is one of the few that has been demonstrated to have extensive device applications. Okay. So I will first start with introducing the institute where I am at. Okay, so VSTEC, the full name is Vittaya Sirit Methi. Long name. Most of Thai people actually cannot pronounce the full name either, actually. So we go by VSTEC. It is a private university, postgraduate level only, master's and PhD. Private university, we were founded by a group of companies, Thai petrochemical oil and gas companies, basically. So PTT is Thai national oil and gas companies, yeah. And they also have subsidiaries that joined into the project. And later, the VSTEC was also joined by other private companies like the big banks in Thailand, as well as many other sponsors, actually. So these are just listing some of them only. Where we are, so this is Thailand. Bangkok is right there in the middle. We are in the eastern part of Thailand, which is right here. VSTEC, we are here. We are in a province which is called Rayong. This part has actually lots of industrial estates. So Chonburi and Rayong, this is the main eastern seaboard where we have the heavy industries, the main seaport, well, including all like the nice islands and beaches as well. And if you search for our district, so we are in Wangchan district in Rayong, you see this photo. So this part, we are a bit further inland, and this part is actually popular for tropical fruits like durians, mangoes, mangosteens. So this part of Rayong is actually more about like agriculture, and we are surrounded by like the old rubber and palm plantations, and we built this university here. And actually, the wider area is part of a project called EECI, Eastern Economic Corridor of Innovation. And EECI and VISTEC, we would like it to be the place where we drive the innovation, research excellence for the next generation of industries in Thailand. So at VISTEC, we have 4 schools: energy and environment, biotechnologies, and digital. And I'm from this school, School of Molecular Science and Engineering. And our research focuses on advanced materials, semiconductors, optoelectronic, electronic devices, and other professors work on like CO2 capture, utilization, smart materials, absorbents, catalysis, and smart polymers, and so on. So if you are interested in VISTEC, you can also check our website, vistec.ac.th. Okay. Yeah, and also we also have the Frontier Research Center where we link with the industries, and also recently the university also founded a company called VisUp, which is a venture builder that invests into startup projects based on the research we are doing at VISTEC. My lab, electronic devices and materials innovation laboratory. So we focus on semiconductors from the basic fundamentals. So studying like what happens when we change the structure, how would that like affect the properties of the materials. In this part, we collaborate with like theorists who use DFTs to do the study into the electronic structures. And then we are focusing on a little bit of the synthesis of new materials and a lot of focus on thin film processing, what happens when we change the processing conditions, all the other factors, how would that affect the thin film properties and then the electronic properties and then the device performance. And we study that by using materials and film characterizations, and also we make basic devices like transistors and solar cells. Okay, so the first question, then why copper thiocyanate, CuSCN? Why are we interested in this material? In the field of like related field of organic electronics and oxide electronics, this one is actually quite recent, let's say in the past 10 years, but the material has been, or at least the structure has been elucidated a long time ago, like in the 70s and in the 80s. Okay. This is how the material looks like. So looking at the structures, actually, we can consider them as coordination polymers. So 3-dimensional polymers consisting of the metal centers linked by the thiocyanate ligands. And as I will mention later in the talk, they can be modified using other organic ligands. That's why we sort of classify them as coordination polymers. And the early studies on these materials was almost single-handedly done by Professor Tanakone, studying about the temperature dependence of the charge transport, what happens when we change the stoichiometry. And the application started to appear in the late 80s and in the 1990s. So back at the very early stages of dye-sensitized solar cells or artificial photosynthesis, right? So how to capture sunlight energy and convert them into chemical fuels, which is also nowadays also a very active field of research. Copper thiocyanate was already explored as a photocathode, so absorb light and then transfer electrons to reduce water, for example. And then the main interest started to appear when Brian O'Regan, who was a co-inventor of the dye-synthesized solar cells, used copper thiocyanate as the whole transport layer, or the solid electrolyte, as it was called back then, in the dye-synthesized solar cells. So normally dye solar cells is based on a photoelectrochemical system. Titanium dioxide sensitized by dye molecules, but it's in a liquid state. So it's in contact with the liquid electrolyte, which transport electrons from the back contact to replenish the dyes after the dyes have lost their electrons. So liquid system has problems about like leaking, right? So researchers were trying to identify a suitable solid state electrolytes or a whole transport material. And copper thiocyanate was used for that application. It showed like quite good performance back then, and very similar structure by changing the organic dye molecules to other light absorbers, like the extremely thin inorganic absorber in these papers, or in quantum dots. But the structures were essentially like very similar. So having a anode and then synthesized by photoactive materials and then use the copper thiocyanate as the whole transport material. For my interest, then back then when I was doing a PhD, so we were actually looking at P-type oxides. So for metal oxides, semiconductors based on metal oxides, the N-types are very good, like zinc oxide, tin 4 oxide, indium oxide, or their combination. So the one that is now commercially available is the IGZO, indium gallium zinc oxide. So these are all N-type. They are highly transparent. They transport electrons very, very well. But to make the useful electronics, then you need to combine N-type and P-type together to make complementary circuits that would actually expand the application areas of the oxide semiconductors further. So people were trying to identify P-type oxides. A few are available, like nickel oxide, copper 1 oxide, or tin 2 oxide, actually. But these guys were quite difficult to work with. Like the first material I started working with was copper oxide, and then we wanted to focus on solution processing to allow a large area fabrication with cost-effective methods. It was difficult to control the oxidation state of the copper. Basically, for copper 1 oxide, you always get mixed phases, and then the performance of the devices was difficult to get it to be high. So then we were looking for alternatives, and then Brian O'Regan was at Imperial back then, and I was sent to talk to Brian O'Regan one day, and we started spin coating copper thiocyanate on the silicon substrates, and then the first transistors like worked almost straight away, although like there was a lot of things to be optimized, but it did really show the field effect from copper thiocyanate, so which is quite amazing. So we optimized the processing and then looked in more details, and we made the TFTs and inverters in the early investigations, and then also together with the postdocs back in the group back then, Dr. Ajay Perumal and Dr. Nia Jakob-Gross, we made also OLEDs and OPVs using copper thiocyanate as the whole transport layer. In this case, it was when we compare with the standard PSS whole transport layer, it was better because it was more transparent. One thing, like this one here, more transparent, so let more light into the OPV. And then it also is very good at blocking electrons. So it allows holes to go through, but then because of the conduction band is very high, it's effective at blocking electrons, so preventing leakage in the devices. Okay, and following that, actually, then it was used in many other devices, and particularly in perovskite solar cells during the early days of the perovskites as well, because also perovskite sort of evolved from the dye solar cells by replacing organic molecules with the perovskite materials in the early investigations. They also investigated the use of copper thiocyanate as a whole transport layer. And recently, we also explore this in photoelectrochemical cells. And as I mentioned at the beginning, actually, it was already used at a very early stage. But now like research in this area is more advanced, and also we explore this as a high work function layer in silicon photoanodes. So adding copper thiocyanate on top of the copper metals, we found that the silicon photoanodes for oxidizing water works better. So it can produce higher photovoltage when illuminated with sunlight. So the unique properties of the copper thiocyanate are based on its electronic structures. The three-dimensional structures of copper thiocyanate actually can sort of be subdivided into the two-dimensional layers of copper and sulfur network. So we see here this structure, if we expand it, okay, into 3 dimensions, actually it forms a two-dimensional layers of copper and sulfur network, separated by the CN groups. Okay, so you can think of them as also like stacked 2D layers, but they're all linked together with the covalent bonds. So with this, then the valence band consists of the copper, the orbitals hybridized with the sulfur, allowing valence band to have a very good hole transport, so quite dispersed. And at the same time, the conduction band is then from the pi star orbital of the thiocyanate, particularly on the CN part, that gives it a very high energy. So if we look at the like reference energy values here, the valence band is around minus 5.5 to minus 5, depending on the measurement conditions compared to the vacuum level. So this is also a very good level for hole transport. And because of the conduction band is like minus 2 eV compared to vacuum level, it's very high. So it's very effective at blocking electrons. And also, with a collaborator, Professor Daniel Packwood in Japan, he also did the theoretical investigations and actually found that this two-dimensional layers of the copper and sulfur also is quite robust when exposed to temperatures. So in this case, the added like some temperature fluctuations into the structures, and then we find that the top of the valence band has very low variation. So in terms of the variation, is very small. The green ones here represents like higher variations in the electronic state. So meaning that the way that the copper and sulfur form into this network, actually it forms also an hexagonal, but not a flat hexagonal, buckle SIG number rings, then actually keep the connections of the whole transport pathway quite well, even when the temperature is even when we consider the effects of temperature. And so at VISTEC, we look in particular about the coordination chemistry aspect of copper thiocyanate. At the beginning, like our perspective started from like inorganic geolytic oxides. We did not care a lot about chemistry, but working with it, we know for sure that it has a lot of problems, because first of all, it's not processable by normal solvents. We need some particular solvents for copper thiocyanate. One of them that we regularly use is diethyl sulfide. So it has a sulfur here, and then the ethyl groups on two sides. And anyone that works with this solvent and this material will know that the smell stays for a long time. Okay, it's actually not a like very toxic compound or anything, because it's actually a food additive as well, and it can be found in like durian, which is very fitting that we are doing this research here at VISTEC, surrounded by durian plantations. Okay, but we have not tried to like distill diethyl sulfide from durians around here to use it. But yeah, from this publication is like one of the components in durians or onions and garlic. Okay. But yeah, when we make the films, we know that the solvent molecules are still there, because you can still smell it even after anneal the films already at like 100 or higher. Keep them in the box. When you open the box, you can still smell something. and this is normally the usual way of producing like all the devices using copper thiocyanate films. Okay. And actually one day, since when I was still doing PhD, when I like accidentally left the vial slightly open, and then evaporation happened, and then actually it forms very nice crystals. Yeah. Okay. And when I came to VISTEC, and then I had a student check what the crystal structure was, and then we found that actually it is a new compound. So the three-dimensional structure of the copper thiocyanate is now modified into a one-dimensional structure. So, and each one of the copper is capped here by the diethyl sulfide molecules. And this one is also reported also quite recently in the literature. So we can see that the diethyl sulfide here, the sulfur is actually a soft donor, and it can coordinate with the copper one centers. Okay. So yeah, for sure, the diethyl sulfide have strong interactions with the copper. Then the first objective we wanted to do was in how can we remove the diethyl sulfide from the films. Okay. Then we try with the anti-solvent treatment, which is also a common method used in like organic and also perovskite films. So spin coat the film first, and then wash the film with the anti-solvents. Like we try CHF, tetrahydrofuran, acetone, methanol, and isopropyl alcohol, and then anneal the films afterwards. So measuring the mass loss, we can see that the this compound here, okay, the compound that has the diethyl sulfides are fully coordinating with the copper. When we measure the mass loss, we see that okay, yeah, the ligands start to go away when we heat like above 100 degrees Celsius. So after soaking in the anti-solvents, we were hoping that okay, the mass loss maybe should be less, right? Because soaking in the anti-solvents, we were hoping that we could remove the diethyl sulfide away. Okay, but actually no, it's either the same or even more mass loss. That was already like something quite surprising, perplexing. And then we also studying the film state. Okay, in this case we try to prove the presence of the diethyl sulfide in the film state using gas chromatography mass spectrometry. So we use a thin mica substrate and deposit the CuSCN directly on the mica, and then because mica is very thin, also brittle, we can just cut them into small pieces, put them in the vials, and then run the GZMS. So yeah, for sure, we find the signal of diethyl sulfide. Yeah. But surprisingly, the same thing as when we tested with the bulk material. So when we treated the film with any of these 4 anti-solvents, we still found the same thing, and they were all identified as diethyl sulfide. We also did synchrotron-based X-ray absorption spectroscopy, and we also found the same thing, more evidence of the diethyl sulfide. And yeah, for some of them, like especially THF and acetone, THF in particular, we find that actually we observe more mass loss on the TGA, meaning that there's more diethyl sulfide. And also when we did the analysis of this X-ray absorption experiment, we also found more of the DS component in the material as well. And when we looked at the structural properties, okay, we find that the thin films became more crystalline compared to the pristine state. So because it's not moving. Okay, the signal on that point there, okay, and also on the outer plane is getting stronger, especially in the THF when treated with THF. So from this, we can also see that the orientation of the films also changed a little bit. Okay. This was like the old analysis when we still identify this one as a hexagonal phase on the copper tar cyanide, but recently we actually find that actually it's a rhombohedral phase. But the directions of the planes are actually the same. It's just that the stacking layers from A B in the hexagonal would be A B C instead. But the overall directions of the planes are the same. So the long length of the crystals are aligned. Okay, the longitudinal directions of the crystals is aligned with the plane of the substrate. So they are lying like in this like long needles on the plane of the substrates, basically. And with the collaboration, we then also look at the theoretical studies. And indeed, the diethylsulfide can coordinate very strongly on the surfaces of CuSCN, especially when the copper atoms are on the top. Okay. Like these two planes actually have higher energy than the other planes that we investigated for the CuSCN. But they can interact with the diethylsulfide, meaning that the diethylsulfide actually can lower the energy of these surfaces. So they come and then bond with the copper and then stabilize these high energy surfaces. And these are the same planes that we found from the X-ray diffraction experiments, basically. And in terms of the film morphologies, the THF, okay, even though like the films become slightly thicker, okay, when we just wash by THF, and the RMS, so it's become smoother, and also the grain size becomes smaller. So from taking all of the evidence together, then we think what happens is this. So the typical route of processing copper thiocyanate using DES gives a film set made of crystallites with low crystallinity and some of the aggregations. Okay. And the diethylsulfides are likely to be on the outside surfaces of these tiny little crystallites. And when we treat with THF, that leads to higher crystallinity of the grains inside and less aggregation. So less aggregation meaning that actually there are more surfaces now for the diethylsulfide to coordinate on the outside of the tiny little nanoscale grains. Some of them didn't work because like IPA, for example, then actually induce more aggregation. And this one here on the left here gives films with high mobility. So the mobility is studied with both time resolved microwave conductivity and thin film transistors. And for both of them, gave consistent results that the THF treatment can increase the whole mobility by like about 4 times, basically. And we did the follow-up work and also explore the applicability of this method in OLEDs and OPVs as well. And then we also found that the device performance became better, like the PCE. This one was still when we were still using like the old fullerene-based system. So PCE increased from 8 to 9. Okay, and also in OLEDs give a higher efficiency. And then following on that, so now we know that the diethylsulfides can remain in the film. And we also did the analysis of the X-ray absorption spectroscopy from the synchrotron-based experiments again. And then we see that compared to like the bulk powder sample of copper thiocyanate from the direct synthesis and the copper thiocyanate after processing with diethylsulfide, drop cast into powder sample, and then anneal trying to get rid of some of the solvent molecules already. When we look at this one here, so we are observing X-ray absorption near the copper KH. Okay, so this gives the information about local structure around copper. So we see that the structure around the copper atoms becomes like less ordered, okay, so more disordered. So in this case, we think that this is because of the SCN vacancies. So what we think happens is that so after spin coating, the diethylsulfide copper thiocyanate is in sort of the wet state, okay? And then during spinning, some of the diethylsulfide leaves, the film becomes like in the gel state. But inside, so there's a mixture around copper of the thiocyanate ligands and also the DES molecules. And before it solidifies completely, right, some of the solvents of the DES molecules still trying to leave. And that basically leaves some vacancy states inside the CuSCN material. And so we try to fill the defect states by using iodine. So iodine is very nice because it's also soluble in the di2 sulfide. Just add directly the solid iodine into the same processing solution. And then we find that after at the optimum condition as well, we can see that the local structure around copper, okay, is restored again. So the iodine, so iodine actually we add as I2, but at the optimal concentration, it's become I minus and then fills in the SCN vacancy. Note that also that the iodine has the same valence state as SCN. SCN is also 1 minus. We also did the DFT with our collaborator, Professor Adisa at Kasetsart University in Thailand. So we look at the perfect case compared to the thiocyanate vacancy case, then we can see that there are it's become like messy, basically a lot of defect states here, especially the donor states. And because copper thiocyanate is p-type, then we don't like donor states because donor would like either produce electrons that would neutralize the holes, or they could become hole killers. And then we also prove from the theory that when we substitute the vacancy here with the iodine, okay, it can reduce the number of the defect states. Like this one here with the SCN vacancy becomes like this one here. There's still like a defect state left, but it's become like much better compared to the previous case. And then actually surprisingly, if we can manage to add the whole iodine molecule to replace that, we could eliminate all of the donor states and actually have a very shallow acceptor state that can increase the p-type conductivity. But experimentally, we have not been able to add this as a whole molecule yet. It separates and then forms like clusters of iodine. This more some visualizations of the defect state. So the donor states here, once substituted by the iodine, then is eliminated. And yeah, the performance gets better. The transistor gradually gets better at the optimal concentration. Too much iodine, then it's not good. Then it's become like defects, actually like impurity defects inside. So adding iodine inside, then from this work, we see that it's actually not a p-type doping, but it's a defect peeling effect. Okay, so it's a defect passivation. We also observe that other device characteristics like become better, like the threshold voltage and also the on-off ratio, and also quite stable compared to the non-treated. Okay, what about beyond copper thiocyanate? So we see that the di2 sulfide, the molecules, right, can coordinate directly with the copper thiocyanate and form like a new structure. Yes, so we then actually my background physics, but then like from this work, then we started to explore about more the chemistry side, and we look at the what is available. So actually, from the structural chemistry, in inorganic chemistry, people already reported many structures of copper thiocyanate derivatives, okay, with coordinated with ligands. And when we compiled this and then did some DFT study. So from the 3D copper thiocyanate, they can be rearranged into many forms. 2D sheets, okay. 1D ladder, this is the same as the one coordinated by copper thiocyanate with the DES, okay, 1D ladder, 1D zigzag chain, or even a monomer. So the CuSCN actually has a great range of structural versatility, okay, and by analyzing all these different structures, and we identify like the 4 factors that affect how we can sort of tune the structure of the copper thiocyanate main network. Okay. The geometry around the copper, this like it prefers to have the tetrahedral geometry, so we always see some undulation. The ratio, okay, if they have lots of ligands, and basically it cuts the number of linkages by the thiocyanate, so it goes more ligands, then we will go to lower dimensionality. And also steric effects would prevent too many ligands to join. And also some of the supramolecular interactions appear to have a major role in holding the two-dimensional structures. And 2D structures are very interesting. This is also one of the main directions that we are investigating right now as well. So we look at the electronic structures. This is actually as expected. So when we cut down the dimensionality from the 3D state, right? Three-dimensional state, the key whole transport pathway is through the copper and sulfur. So this one forms an extended two-dimensional layers, as I mentioned earlier. Right? And when we cut the structure down to 2D, then this copper and sulfur network still retain as a 1D, as a one-dimensional substructure inside. And so it still shows some dispersion, some like possibility for whole transport. But if we reduce the dimensionality down further to like 1D or 0D, we can see that the valence band becomes like narrower and also flatter. So meaning that the whole transport is now gone, basically. The properties are deteriorated. And another interesting thing is also the interactions between the ligands themselves. So the gray lines here are the states formed by the ligands. In the 2D structures, some of them can have strong pi-pi interactions actually. And maybe it is possible to also have some sort of electron transport through the organic states. So then we can have whole transport through the copper and sulfur network, and the electron transport through the interactions among the aromatic rings within the 2D sheets of copper thiocyanate derivatives. And we also see the systematic variations, like from the three-dimensional case, when we reduce the dimensionality. This is because there's less interactions between the states, the electrons and holes become more localized, then the band gaps become wider, and also the bandwidths become narrower as well. And so right now we are looking at ligand modification. Like this is an example of another group. So when they modify with the aromatic ligands, actually can also tune the optical properties. Copper thiocyanate is good for transparent electronics, very large band gap, very transparent, but maybe it's a bit boring. But if we add some aromatic compounds, we can also tune the light absorption and light emission of the copper thiocyanate. And also this two-dimensional network of the copper and sulfur is of interest, and also the two-dimensional layers of the copper thiocyanate structures themselves as well. We now, like with Genipat, we can also use pyridine molecules to make the 2D structures like reliably. And now then the research question is in how can we make the films and also retain the two-dimensional structures within the films. And also for a broader context, coordination polymers, okay, not very well known in the field of organic electronics or oxide electronics yet. But in the fields of chemistry, they have been investigated for a long time, especially in the field called metal organic frameworks. So metal organic frameworks can be thought of a subset of coordination polymers. They are essentially coordination polymers with like larger ligands that allow structures to have poles inside. But in terms of the coordination polymers, not necessary. The poles are not necessary. So only quite recently that some of the device applications of these coordination polymers start to appear. Some of them also form very strong like 2D structures, like this one is here, and CuBHT. This one is a benzene ring with 6 sulfur and then copper, so forms a two-dimensional layers. Also high conductivity. So this one basically represents a emerging field of optoelectronic applications based on coordination polymer semiconductors. And yep, so this is like the end of the talk now. So I would like to thank all the funders, the Thailand Research Fund in Thailand, because of the higher education in Thailand Science Research and Innovation, National Research Council in Thailand, Program Management Unit for Competitiveness. And recently we also got a research grant from the US Air Force Office of Scientific Research and all of my collaborators from all around the world. Actually, this photo is not quite updated. This is like maybe 2-3 years ago. Yeah. And thank you everyone for joining the talk today. And thanks again to Costas for inviting me.
Thank you very much, Pete, for the talk and the contribution. Thank you. If you would like to stop sharing the screen in order to check if there are any questions.
Okay.
I have a couple of questions. Georgios, you would like to ask a question?
Go ahead, Costas, go ahead.
No. First you, please.
Well, thanks a lot for the presentation. You mentioned at the end of your presentation about going to quasi 2 and quasi 1 dimensional materials, I understand.
Yeah.
So how do you create experimentally, and what do you mean by 2-dimensional sheets and 1-dimensional structures?
Okay. Let me reshare. So by modifying the copper thiocyanate, essentially intentionally adding some ligands to the copper thiocyanate. When the ligands coordinate with the copper, they can actually generate different topologies or different dimensionalities of the structures. In this case, for example, actually using this one here or just pyridine, if we can control the ratio between the thiocyanate and the pyridine ligand to be 1-to-1, it would form into a 2-dimensional sheet of the copper thiocyanate. Okay. So the parent structure is like this. Right? And then when there's an extra ligand, it would compete with the thiocyanate ligands basically. And then it would link or like cap on one of the side of the copper. In this case, it would form quite a flat 2-dimensional sheet. And other structures are possible depending on the ligands that we choose. Like if we choose chloropyridine, 3-chloropyridine, and this case is also a 2D because this one here expands in 2 dimensions. Okay, and there's no bonds between this layer and the next layer because they are capped by the pyridine derivatives here. It's not like a flat 2-dimensional sheet, but it's a layer structure, 2-dimensional layer structure. And also if we add more, they would form into like a 1-dimensional layers like this. So this one here is extended in 1-dimensional, and then there's no bondings between the one chain and the other. They can still form into the solid through like intermolecular interactions, but there's no like strong covalent or coordination bonds. So these structures have been reported, but most of them are sort of the curiosity in terms of structural chemistry. So right now we are trying to make them more reliably, and then trying to find ways to process them into thin films. Yeah.
Thanks a lot.
Thank you.
Pete, I have some questions. First of all, I would like to ask you, how do you manage the functionalization or the modification of the copper thiocyanate material? I mean, are you using chemical methods, or do you think that optical methods can be applied?
So far we have only tried like chemical methods. So we Like in all of this, basically, many of the ligands are in the liquid state, or if they are solid, we can also just dissolve them and then add the copper thiocyanate and the ligands together. And then varying some conditions, then the ligands would coordinate with the copper. Optical modification. We haven't really tried that. One thing that
especially in the 2D case, I was thinking
yeah.
about this. Why I'm thinking about this, because also, you know, I mean, if you think the example of graphene oxide and how do they reduce the graphene oxide using lasers, you know, I mean, for example, is this, you know, something that has been demonstrated with this type of material in 2D phase?
Oh, I don't think anyone has done it, but that would be interesting. And also, it would work if we choose the ligands that can absorb the correct wavelength of the laser. Yeah. If the copper thiocyanate itself, I think the band gap is too wide. You would
Yeah,
need
I mean, with the
UV
ligands,
lasers.
that's why.
Yeah.
And my second question is like, recently, Thomas has published, I think like before, not recently, I mean before 2 years, they published a paper that they used this copper thiocyanate as a gas sensor. And I suspect that, you know, the gas sensing comes from the gap of any of these ligands. So the dopant or the agent that they would like, it was, in this case, it was hydrogen. I think that interacts with vacuum places of a ligand. Do the ligand affect a lot the conductivity of this material?
These ligands, depending on the amount, actually, you add too much, the conductivity would be very low. And because I think in that paper he was looking at hydrogen sensing, so the structure of the copper thiocyanate actually I think has enough space for hydrogen to go in anyway. Like this like gap, for example, the pore within the structure. This is like carbon, nitrogen, and also sulfur and copper. So these are quite big, and the hydrogens are quite small. So hydrogen can definitely go inside.
And how do you think that they interact? Because they observe it was like an electrical response sensor. So when they had the hydrogen, you know, the conductivity changed, and when the hydrogen was removed, the conductivity restored back to its initial state. And I was wondering, I mean, in the case of the perovskites, they interact with, we suspect that they interact with some vacancies. But in this case, and you're right, I mean, they intrude, you know, the gas intrudes through the porosity of the material and interact with the platform. But in this case, I was wondering what is the main mechanism of this sensing. And when you are presenting, I thought that probably it was somehow interaction with any type of vacant position of the ligand, but probably this is not the case, as you.
And I think it's also possible. The porosity allows the hydrogen to diffuse through the material, and I think there are not just the thiocyanate vacancies, but also I think there are copper vacancies inside as well. So I think there are any of the incomplete bonds would be active sites for hydrogens to interact. Yeah.
Yeah. And my last question is like, compared to the graphene-based electrodes, what are the advantages of or the disadvantages of the copper thiocyanate?
So if in terms of electrodes, then this one does not have very high conductivity, but it's good to bridge the semiconductors and the electrodes, basically. And also when you want to have holes to go one way and not electrons. Like if we go back, in this example, for example, in the photoelectrochemical cells. So in this case, we would like to use only the holes to oxidize water. And if electrons also go that way, that reduce the efficiency of the device. So we add the copper thiocyanate on the outside, yeah, and then it allows the holes to go while blocking electrons.
Mhm. Yes.
So it's good for whole transport in particular.
Yes, yes, yes. However, also the graphene or the graphene oxide, if you dope it, you can, you can modify its end properties or the whole transport properties or the electron transport properties. I mean, this is easily adjusted. But I can understand that this is like mainly a p-type electrode.
Yeah, mainly for p-type, and can be doped as well. Like recently, like the one we tried with the iodine. So that one actually we found that it doesn't have a strong p-type doping, but when we use other materials like the copper chloride, tin chloride, we can also see some p-type doping effect. And I think maybe also from Thomas's group that he used chlorine gas, directly treat the material with chlorine gas, and then it p-dopes the copper thiocyanate quite strongly.
Mhm. Thank you. Thank you very much, Pete, for this. And I have a last question. Do you have a feeling that this kind of materials, the copper thiocyanate, we can improve somehow their sensing properties? I mean, what is your feeling? How we can change, these sensing properties of these materials? How we
I
can
think
modify? I mean, in the sensors, there are a lot of parameters, the rising time, the fall time of the sensor. So how fast interacts and how fast de-interacts with the sensing element. Do you think, or do you have the feeling that this kind of materials, we can play around a little bit in order to check the dynamics of the sensor?
okay, good point. I think
And let me also ask you a second question. Don't worry, we can discuss this later, or we have to study a little bit. I mean, these materials can be shipped. So can you make this material in Thailand and you can ship these materials to us in order to test them as a sensors or to test, their stability in various temperatures? Recently, we have bought a gas element, a gas chamber that we can change the temperature, but also in the future we can pass different gases. So we have this now this kind of equipment in our university and in our department. I mean, if you make this a material, do you think that it will withstand, the transportation time to come to Crete?
I think it could be safe if we find ways to refrigerate it. We know that if we leave it at room temperature for too long, they will lose the ligands. So basically, they would convert back to the copper thiocyanate. But it also depends on the types of ligands. Like when we look at the pyridine derivatives, actually the strength of the interactions depend on the functionalization. So yeah, some of them that we found actually are stable to quite high temperatures. So yeah, some of them would be stable enough to send over, but maybe to make sure that it stays that way, then we can have some like protective measures, like maybe inlet gas, and also try to chill it down.
Okay, all right. Okay, we will be in contact. Thank you very much, Pete, for your time, because now in Thailand it's late or late afternoon, and for the honor.
Yeah, it's okay.
Thank you very much, Pete, and we will be in
Thank
contact.
you for the invitation again, and thank you for all of you for joining the talks. Yeah, very interesting discussions that we had today, and yeah, look forward to visiting you in Greece.
Whenever you want.
Yes.
Thanks a lot.
Thank
Bye.
you. Bye
Bye.
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 Thank you.